Hi everyone, I'm Zhao from North Carolina State University. I'm glad here to present my work leveraging AI ecosystem for portable and sustainable HPC, GPU kernels in HPC. This paper addressed a fundamental productivity issue exists for a long time. Yet that how to efficiently build customized kernel in different GPU platforms in HPC domain. Currently, the AI ecosystem has proposed Triton, which is perfect suitable for such a need. And let's see. For decades, the GPU computational capacity has evolved a lot, which makes the modern supercomputers more and more relying on the GPUs. And different vendors provide series of GPUs and the corresponding programming interface to fully unleash their computational capacity. But due to the variations of different GPU vendors, GPU architectures, and GPU generations, the GPU kernels are not generally considered as portable and sustainable. If you want to leverage new features or even adopt an existing kernel from one architecture to another one, you need to manually rewrite it. You need to learn their programming interface. And for example here, as shown here, for 5% of hot kernels, which takes over 95% of execution times, they are worth trying to manually rewrite tune, validation, and then deploy. But what for the remaining code kernels, which can take over 95% of code base, but just take 5% of execution time? This still requires manually rewrites previously. But currently saying we have AI agents, they can do the rewrite, but they cost for tokens. They still need some effort. And fortunately, some vendors has recognized that, and even the AI community and even the HPC communities recognize that challenge. And they propose, for example, the heap compiler to directly translate the CUDA code to a ROCm code and make it runnable in this stuff. And even the Cocos and SQL, which is a cross-platform, C++ based, relying on the template technique, portability interface, but they still fell short because they are strongly typed. They cannot aggressively do the memory layout management, and they cannot change anything about memory. They can directly, what they can do is doing the coding, picking which instructions you can do. And the AI community has faced such a challenge as well. Previously, in PyTorch 1.x generation, if you want to build a new module with new operators, you need to manually write in CUDA, in ROCm, and then register it in the eager mode, and then call it in Python. This process is painful. It requires you to have a deep understanding of the operator itself, as well as the GPU architectures, and even the build process. Fortunately, the AI community, after the billions of investment, they proposed a series of Python-based domain-specific languages to handle those stuff. And as a representative of them, Triton has its unique advantage. It provides modularized components in different layers for high-level abstractions of describing the algorithm purpose, and then automatic memory management, architecture-aware code generation, and capacity of both just-in-time and ahead-of-time compilation. The different layers provides both macro and microscope compilation optimizations, which performs automatically. And the vendors can easily provide new hardware support via just providing their own Triton backend to leverage the existing optimization techniques. And for example, in NVIDIA's architectures, they introduced the first generation of Tensor Core, the TF32, the sparsity is the synchronized memory copy, the TMA, and the transformer engine, the low bit. In every generation, they are evolving in every generation. Users need to manually rewrite every line of code if you want to take advantage of those new hardware features. Triton can do this all by one click. They are automatically implemented in a compiler middle end. If the compiler can tell what you want to do from the high level of descriptions. Yeah, and now the optimization process within Triton can recognize typical tile-wise and element-wise operations to automatically apply those optimizations and those new features. And there is a example of traditional HPC compile pipelines versus the Triton compilation pipelines, and which will show in which level you need to do which kind of optimizations. Traditionally, you need to do the tiling, the vectorization, and manage memory where you want to put in shared memory, put in L1 cache, the localities, the dependencies, and schedule the tiles. You need to do all of them manually, and then downgrade to LLVM IR or other IRs. Let the backend compiler to select which instruction you want and do the registers allocation. This is a painful path, but with Triton, as far as you can see, the compiler can apply those optimizations in different layers automatically, and which is extendable. If you want to perform optimizations corresponding to sparsity, you can take advantage of MLIR stuff, because TTIR and TTGIR, they are basically the dialect of MLIRs, and which makes Triton super extendable. And this is an overview of current optimizations versus in existing frameworks versus the Triton from AI community. But Triton ships with Python. It is highly bonded with the PyTorch techniques. It requires you to import Python, use Python as the interceptor, and in the runtime it needs the JIT compilation, and which is far away from what we want in HPC community, because HPC is so complex, and the management of permissions in HPC or environment in HPC is much more complex as well for security. You cannot simply import Torch in a highly restricted supercomputer. So the gap is here. You need to, if you want to take advantage of Triton, you need to import Python. You need to import PyTorch. But we don't want it, so we propose this tool to eliminate all of those dependencies by 3 different layers. From the very beginning, you can manually rewrite your customized kernel from CUDA or from heap, from SQL, directly to Triton, but currently you can do it with your coding agent, and then providing with our framework with some necessary signatures, just like the function signature, the layout of your tensors, and then we can do a ahead of time compilation, and then we wrap it with a wrapper, C-style wrapper, because Triton will generate the PTX or SAS or Kubin, which can be dynamically loaded by the driver functions, as well as the AMD stuff and Intel stuff. And they all provide corresponding functionalities to dynamically load a compilation result. And then with the wrappers, we get templates of those driver functions, and then pass through the GPU pointers to the compiled result, the compiled kernel from Triton. And then it will eliminate all the dependencies from Python, because Triton's result only requires you a row pointer or some scalars just directly in the function's signature. And then it's perfect. It works. It eliminates all the dependencies from outside. And then you can treat it as a single SO or object file. Whoa! It works for HPC community because it's clean. It's one-click linking object, and we kept 3 capabilities of embedding in those for the Triton compilation results, which is PTX, Kubin, and FatBin. We use PTX as default, but there is a trade-off because PTX is not binary. It's assembly. Instead of assembly, I would say it's an IR. And once you want to use a PTX function without binary, it will trigger a recompilation. But PTX keeps the ability for human reading. You can still debugging within them. You can read the purpose. And if you don't want to pay the price of just-in-time compilation, you can choose to use Kubin. And if you want to keep the balance of them, you can use FatBin. But FatBin, why it's called Fat? Because it's much more bigger than others. It contains the PTX, both as well as the binary files. So once the target is different, you need to trigger another round of recompilation. Yeah. One more thing about Triton. Triton has its own benefits. During developing, GPU kernel debugging is painful. Previously, you need to use print in your kernel, and you control the flags. You control the flags which thread you want to get inside. And a few years ago, they introduced the CodeIGDB, but it's still hard to use. Triton has its own advantage. Triton can simulate, just like a simulation, it can run your kernel code directly in CPU with the standard Python debugger. You can directly use the debugger to see what happens inside the tile. Is that the purpose you want? Is that algorithm working correctly? If it is correct, it should work correctly in your GPUs. And that's why we keep the PTX as well, because during the integration, you still need to make sure the wrapper does it work correctly. Yeah, you need to get inside to read what happens. And with those techniques, we successfully did some evaluations on that. We select 3 representative kernels from knowledge, which is the proxy application of Lagrangian hydrodynamic simulations. including one gather kernel and two reduction kernel, and we count the performance via an inside compute as the cycles, kernel cycles. The results shows very interesting reason. For the gather kernel, in the tiny grids, the Triton introduced some redundant control flows, and which makes the actual computation, actual memory traffic, less part of the entire execution time. But when the grid grows to a bigger one, the Triton's performance comes uniform with the native CUDA's implementation. And for the reduction kernel case 1, it calculates some scalars in the very beginning, which is not tile uniform, and then which leads to a little gap between the native implementation and the Triton's version. And the last one, which is highly tile uniform, and we see the reduction performs far way better than the native version. And also, we evaluated this by, can we build a library? Can we build a lib, but directly based on the Triton? And we find it's possible. You can write a series of Triton kernels and then fuse them together and use our framework to compile it as a standard long object file, which provides as a library, and then you call this library. During that, we evaluated with the application a tensor contraction from quantum chemistry, which performs tensor contraction to two of order four dense tensors on one rank. I would say the H7, and it's a GMM like operators, but requires transpose, and then do GMM, and then transpose back to the result shape. The entire kernels are built on top of Triton, and then we compile it as a standard long library. The results shows very promising one. I'm choosing the worst case, because better case can be found in our full paper. That we use only Triton source. We use Triton source code against the code tensor and the heap tensor implementations. In most cases, we get comparable result. Sometimes 10% drop, sometimes 10% increase faster. And what we found very interesting is that Triton can keep the ability of kernel fusion, which if you're using the vendor's library, you cannot. Because Triton, if you write 2 kernels or 3 kernels in Triton, if you want to do a kernel fusion, you can it's easy. You can just write a new kernel and then call those kernels in your new kernel and add a decorator in the new kernel to define it as a Triton kernel. The Triton compiler will say, oh, it's an entire Triton kernel. It will directly perform the kernel fusion. And most benefit we get from the tensor contraction is from the kernel fusion. And additionally, we evaluated, is it possible to directly build an entire application in Triton? We choose to use Access Bench, which is Monte Carlo nitrogen transport benchmark, and it has its own metric of performance, which they call lookups per second. This application is highly diverse. Every single thread will work on different on different elements and which requires different input data and different iterations. The result tells the truth. Yeah, we got a huge drop because Triton is heavily oriented for a tie uniform pattern. And yeah. And that's what Triton foresaw today. For the irregulars, you can get the right result, but the performance drops a lot. But and for the static loop bounds, because of the syntax, Triton requires them to be declared at the very beginning. And the Triton itself, the syntax of Triton, lacks of low-level control to every single thread. You can only perform those control by the masks. So to resolve that, the AI communities, they introduce a slightly lower abstraction of Triton, the Gloom. They provide all the things. You can control every single thread. You can control the dynamic control flow, and it's possible. It's not a barrier. It's possible. It's not a barrier. Cannot be solved. And we are on the way to evaluate that. And in the future, I would say this work is promising because it can leverage all the existing Triton optimizations for the scientific computings. And if we build some new abstraction layers or saying optimization layers like previous presenters in sparsity, it's possible to directly write Triton kernels for sparse contractions or sparse decompositions. Yeah, so leveraging those stuff is not only possible but also applicable. And we want to extend the possibilities of kernel fusion automatically and the entire tool chain of integrating the source code, Triton source code to the HPC environment. As far as you can see, agents take over everything, how to automatically loop that. And for some other evaluations on the broader coverage, they are still on the way, but I would say it's promising. I'm glad to take any questions from you. Thank you.
I'll take one or two questions, please. Yeah. Yeah, Rich.
Is your experience with Triton as a tile-based programming abstraction really sort of mixed results, right?
Yep.
So it's kind of maybe an indictment, not so much of the Triton compiler,
Yep.
but more of the tile programming abstraction. And does that say anything about the utility of the NVIDIA QTile or other tile-based programming abstractions? And if that's the case, what is the right abstraction to achieve good performance for HPC?
Yeah, I would say the abstractions matters mostly in current state is the memory cost. Currently we all agree that the GPU's compute capacity is growing much more faster than the memories. The all bottleneck, you can consider it as memory bottleneck, especially the throughput. And GPUs, they have different abstractions of memory scopes. How to tell the valuable memory objects and where it should be placed. That's the question. And we have some under review work on that to measure, I call it the memory intensity, and to measure how important the memory is, and which is extendable to Triton stuff.
Let's thank Yanbo and speakers may please set up. Yeah.